Alright, so welcome back again. My name is Jesse, and in this wonderful and exciting tutorial, we're trying to see how to do predictive maintenance with machine learning. So what do we mean by predictive maintenance? So predictive maintenance is a strategy, it's a method in which we try to use data from sensors or any historical records or telemetry to predict potential equipment failures or breakdown, right? So in other words, if we have a tool or a device, so it can be an airplane engine or an airplane itself, it can be a car engine, can be a motor, a ship motor, or any form of device, it can be a wind turbine or a solar panel, and then you want to avoid breakdowns, right? How do you reduce breakdowns? So every tool, one way or the other, is going to break down, but how do you let people know that, okay, this is the useful life, this is how powerful the tool is going to last, this is how useful the tool is going to be, this is how long the tool will be available before it breaks down, right? So how long the tool will be available, so we call it as availability, and then useful life, right, of the tool. How long is it going to be in performance? So in order to do that, first you have to collect some data, right? So you can collect data through sensors or through telemetry or through IoT devices, and then when you collect this data, the idea is that by placing sensors and telemetry and IoT device, you are monitoring the device, right? You are monitoring the device till there is a breakdown. So if there is a breakdown, you collect that information as historical data, right? And then you collect that information. So you just collect all the information as historical data. So you have all the data from the sensor, and then you also take let's say the type of breakdown, or when there is a breakdown, and the type of breakdown, right, or type of failure. So you collect all this information from your monitoring, and then once you collect all this information, you try to devise a way in which you can predict, okay, when is going to be the next breakdown, right? So that is the whole idea behind predictive maintenance. So the first thing is that you monitor the device using sensors or telemetry, and then you collect that information, and if there's any breakdown, you write it down, when there is a breakdown and a type of failure. Then from that, you can now do some data analysis and feature engineering. You build a predictive model or machine learning model from that, and then you can use to do predictive maintenance to be able to predict, right, why and when there's going to be a failure, so that you can avoid it. So in the same idea, we have different forms of maintenance. So the first one is that we have corrective maintenance or reactive maintenance. So you check the device, you monitor the device until there's a breakdown, and when there's a breakdown, when there's a failure, you go and then you maintain it, you go and repair it. That is reactive maintenance. And this is important because by doing this, you gather information if you use sensors and telemetry, and then you can gather this information so that you can reduce your corrective maintenance. Then the other form of maintenance we have is preventive maintenance. So preventive maintenance is whereby you have a planned maintenance. So after every 3 weeks, go for a checkup, right? After every 5 months or 1 year, you do a regular checkup, and then you try and see if there's any mistakes anywhere, any failure anywhere, any breakdown, then you maintain it. That is preventive maintenance. Then we have predictive maintenance. So predictive maintenance is all the information you are gathering, so all the breakdowns you have been getting together with all the historical data you have gotten, you can now analyze them and then build a machine learning model or a statistical model to predict when there's going to be a breakdown and then the type of breakdown. So let's see how to do this kind of predictive maintenance in Python. So these are too much of the talking. I hope it's not too much talking. I'll go back again to my space, which are going to be here. Right, so we are using a data set from machine learning UCI library. So this is called predictive maintenance data set, and this data is a real predictive, it's not real, but it's synthetic data set that reflects real predictive encounters. Then we can use to do classification, right, and then regression. So classification is when the type of failure, right, and then regression you can know when, right, or yeah, mostly if it's multivariant or univariant. So this is how the data set looks like, and based on this, you can see that they are taking information about temperature, they're taking information about air temperature, process temperature, because these are systems that are always in an environment, right? And then you have to measure the temperature and the rotational speed. So for example, if you take something like a turbine or an engine or an airplane engine, there is always a rotation, right? So you have to also measure those ones. That's why we have rotational speed, right? The speed, the torque, the two-way, right? And then machine failure. So this is in case there's a failure. Okay, this is what is recorded, right? And then we have TWF, HDF, PWF, OSF, right? So PWF is power failure, and then we have the rest, right? So this is random failure, this is overstrain failure, and then the rest. So let's see how to use this information to do predictive maintenance. So I'll go back again to my workspace here. So apologies for how long this tutorial is going to be, and let's start from scratch. So these are the data sets. I'm going to go back again. I already have the data sets. I'm going to load my EDA packages, which in our case is going to be, let me make it bigger a little. We make it big, right? Import, going to import pandas as PD, and then import numpy as np, and then we also want to load the database packages. It's going to be import cborn as sns. Then we also want to import matplotlib.pyplot. You can use any of the AI agent to help you do that, but let's learn the hard way, right? PLT. So this is the tools we'll be using, right? And then now we will first do some data preparation. So first we will load the data that we have, which in our case we have the data set here. So if you go back, it's going to be my A1, this is the name of the data set, and then you can just check the data set that we have. So if you check this data set, you can see that this data set has the UID, the product ID, right? Because in case you want to do predictive maintenance, you are not just measuring only just one turbine or one engine or one airplane or one device. You have different devices, right? And different devices have different naming and labeling. So these are the product ID, right? Together with the unique ID. And then you have the type. So the type here means this is M, medium, low, high, right? The type of failure, whether it's a medium failure, high failure, or low failure. Then you have the air temperature, the process temperature, because you have to measure because they are in the environment. The rotational speed, because these tools are rotating, right? And they have a speed within them, and then the rest. So these are the main information, and you can see that these ones here, so the TWF, the heat dissipation failure, power failure, OS failure, RNS failure, these are the types of failure. So we can convert these ones into classification, and then this is the main failure. So let's do some checks to see if there's missing data. So it's going to be, we want to check for if there's a missing data. So df is going to be pd, not df, but df.is no, right? You want to check if there is a failure. Yeah, if there is missing data. And then based on what we have here, there is no missing data within this data that we have, right? Since we don't have any missing data, we can now do the descriptive analysis to see how the data set looks like. And with this, we can see that we have the minimum and maximum standard deviation, and then this time we can also plot them out. So I can simply do a simple plot of this entire stuff by going with df.his, and then let's give a figure size of, let's say 1010 is okay. Then this is going to print it out for us. So we have the structure of the data, can see the distribution of it. So this is not important, you have to take it out, but you can see the curve, right? The same for the temperature, for the process temperature, and the rest. Perfect. So that is the first thing. Now we need to do some class distribution, and then based on what we have, we realize that we have a machine failure, right? Failure column. We had a machine failure column. If I go back and I just do the unique, you can see that we have just 2. So 0 means that there is no failure, 1 means that there is a failure, and then based on this we can now plot, we can do the value count. And in most cases, right, most devices are expected to not fail, right? So most of the time, if you get data like this, there's going to be very little failure, right? We build tools for them not to fail. So in most data sets like this, the number of failures are always going to be less, right? The number of failures are always going to be less. So sns.count plot, and do s is going to be the machine learning, or no, machine failure. In most tools, we don't build tools for them to fail, right? So this is okay, but you can also correct it. So you can see that the failure is just very little, right, as compared to the non-failure. Perfect. Now that is the count plot that we have done. We can also create a class type of failure, right? So we can do the same thing by just building a simple option here, because if you check our data set here, we have these all are types of failure. So we need to copy these ones, and we need to build a function that gets them. So let's say get, or you can call it as the classify failure type. This is not the machine learning model, but this is going to be used to map these columns, right, to map them to the different types of failure. So that's the main idea behind this. And then we can simply do something like this. So we get all of this here, and then we need to get the failure column. So the failure columns that we want to use here is these ones. All of this is a failure column. So these ones are our failure column, because that's what we want to map. Right, so this is what we want to do. We want to use these ones to map for our failure, right? So we have a simple function like this, and now we can apply this one to our data set. And if I apply it to the data set, I can have something like this. So df failure type, it's going to be my df.apply. I want to apply this one to the particular column. I want to apply it to the column on the x-axis, right? So axis, and if I run this one, it's supposed to be x without this, right, because we're applying. And if I go back here, if I check this one now, we have these ones, right, no failure, no failure, and we can now plot this one out. We can do a count plot as we did earlier on for this one, to be able to identify the plot. So you can see from here we have the no failure. As I said, most devices are built not to fail, right? So yeah, that means that it's a good machine, right? And then we have the power failure, the remaining types of failure, random failure, heat dissipation failure, and the rest. This is not balanced, but we can work with this one, right? And then we can now move on from here, and we can also do a different type of classification, because notice that we have some class distribution for the type here. So medium, type, and then a medium, low, and high, different types of machine failure. Perfect. So since we have this one, we can also do some kind of plot, right? So let's try another plot. We can also do, we can do another plot to identify the temperature and the process temperature against the failure that we have, right? We can do this kind of plot, which is going to be my seaborne, not. Then you can see that it's going to give us a very nice plot in which we have the different types of failure together with the temperature at which they fail, and then the process temperature. So this is a very useful information that allows us to know that, okay, around this temperature there are no failures, right? But there is a failure here, and this is a power failure. There's also another power failure here. There's also another power failure here, right? So this is very informative to know, like a form of a scatter plot, right, which is useful. Perfect. Then we can also have some more things we can also do, right? We can do another scatter plot to allow us to point the different forms of failure. If I go back here with this simple function here, I can now run this one, and this is also similar to what we have above, right? But now we can see that based on our entire data set, which of them fail based on the air temperature and then the process temperature. So this is one way. We can apply the same logic, not just for the temperature, but you notice that we also have rotational speed and torque, right? We have two where the minimum, right? Minutes. You can also do the same kind of plot for these ones. Perfect. So let's move on from here. We have seen some analysis to be able to identify the key features there. Let's move on from here to do some other form of analysis, right? So I'm going to go back here to what we have done so far, and then we can also try and see and do a outlier detection. So I'll go back here. And then one of the ways we can do outlier detection is to use something like, let's say, a box plot, right? We can use a box plot to do outlier detection. And then what you are doing is that we're going to take all the temperature, the process time, the rotational speed, and the tool, and then we can now run this one here. So if I run this, you can see that based on the temperature, most of them are within the range. So you can see that there are not a lot of outliers here. So there's a normal range for the machine, the same for the process temperature and the air temperature. But when we come to the rotational speed, most of the data sets are outside the normal range, right? The upper quartile. So you can see that these are all outliers, right? So in the rotational speed. And if you go to the torque, so there is some below and some above. So you can, in case you want to make some prediction, you have to be understanding that, okay, most of the errors that will be coming will be something from here, right? So the torque and then the rotational speed will also influence it, right? Okay, later on. So this is another way. So we can just do some simple narrative, and then in the narrative we can say that we had the torque and then rotational speed had more outliers. Or points outside their normal limits, right? Or normal range or quartile, whatever you call it, right? Perfect. So you always be considering this later on in the future if you want to do some analysis. Perfect. Now let's move on from here to do some feature engineering and then machine learning, right? And ML. So how do we do that? So this is the next step. So you have understood how our data set look like. We know that based on this, these are the place we can get outlier. We have seen how that there are more no failures than failures. We have seen the different types of failure that we have. Then we have seen the different levels of failure, right? Now let's move on from here and do some feature engineering. So first we will just get all the columns that you want, what we need and what we don't need. We can do more feature importance, but let's skip that because of the time. And from here we can see that we have these columns, right? So we can map this one, we can encode this type to allow us to know the priority of it. So I can just go back again and encode this one. One of the ways we can do that is, since this is, I go with this option here, dot unique, you can see that this is MLT, so we can actually map them and then convert them into, we want to map them and convert them into like a normal encoding, right? So we can simply do something like this to do a simple encoding for this one here, so that it is encoded. And now since it is encoded, we can now copy this entire stuff here from here till here to be our, we don't need a product ID, this is not important, to do our features. So it's going to be our features, so df, or I can just call it as my feature columns. So these are all the feature columns that we need for our data set. right? And then we can now go back from this place and do my S features. It's going to be my df, then feature columns. So this is going to be our feature columns, and then our Y labels is going to be, so here we can do the machine. So this machine can be used to predict, so it's going to be binary, right? Or we can also use the failure type as multi-class, right? So we can use this one to do some simple prediction here. This can also be used, right, in case you want to use this particular format to do normal binary. So this is going to be binary classification. And then we can now split our data set. So since we have gotten it, we need to split the data set. We have to from scikit-learn. You can use neural network, but we'll be using scikit-learn in this case for our work, right? Because scikit-learn is good. And then we can use different models to help us with that. So we will just load all of the libraries. So using scikit-learn, linear model. You can also use different models, right? But these are what we are using. And then we have confusion display. Perfect. So let's build our simple model. So first we'll split our data set, because it's important to split to have test string. So this is going to be our data set. So you are splitting these features by, this one can be 25, it can be 30. Then we can now build our model. So let's do the training. So I'll create a simple function and I'll call it as build model. And then this one will take in the classifier. I'll call it as classifier, right? And then the classifier will just take in the string, and then a Y train data set. And then we can now bring a simple option here. So classifier dot fit s train Y train. So this is our data set, and then we can now return the classifier. So by this option here, we can simply build any model and then return it out, right? So we have something like this. So we have the classifier that we have, then you pass it here. So let's build it here. So I'll just go back here, and then let's build our first model. It's going to be a random forest model. So we can just go with my RF. So RF is going to be my random forest. Then I need to specify the number of estimators in case I want. Some of them have parameters, some don't have, and let's make it just as 100. And then we just specify the random state. So this random state means that if you also want to get the same values, you specify the same number. And now we can build a model. I'll call it as RF classifier. Then let's go with this option here. So this is going to build a model. It's supposed to be RF, right? Yeah. Perfect. Now we have built our model. So let's check the accuracy of the model. To check the accuracy of the model, we can just do the RF classifier dot score. Then I'll pass in my S test and my Y test. So this is going to give us an accuracy of 0.95. So the 0.95 is always going to predict this amount, right? So this is the accuracy of this model. So it is very good to predict those that are not going to fail and those that are going to fail. We can also apply the same thing for a logistic regression model. So let's do the same thing for a logistic regression model. But before we do that, we have to do model evaluation. Evals, right? And then to do model evaluation, we first have to, this is a form of model evaluation. We can do the normal classification report. And then the classification report is going to take in my S test or my Y test. And then my Y predict. So the Y predict is mostly, we take the model. So let's do it like this. We take the model, then we just use the model to predict. over the S test, right? And then this is going to give us our main model, right? And then I can now do my Y print, and then this is going to give us my classification report. And as you can see, we got 0.99. So the reason this is very high is because the data set looks not balanced, right? As you can see from here, but in most cases it doesn't look balanced, right? You saw from here that's not looking balanced. So in most cases this is correct, because like we mostly don't expect machines to fail, right? But in case you want to balance it, you have to automatically create a balanced data set so that you can predict perfectly the failure. Okay, let's go back from here, and we can now do some confusion metrics. So I can simply do a confusion matrix of what we have here. Confusion matrix allows us to know false positive and false negative. So in this case, it's going to be my RF classifier, and then we will now do the same thing for the displays. Then I can now print this one as my display dot plot, and then plt dot show. So this is going to give us the false positive and the false negative. So you see the true label and then the predicted label for this our data set, right? So 0 is no failure, right? So most of the time it will be predicting that most of the machines are not failing, and this amount of times it will predict that there is a failure. Perfect. Let's do another model. So we're trying a different model. So the model we're trying is a logistic regression model. So which is going to be this option here, and then we can now do the LR CLF. It's going to be my build model as we did above. Same thing we did here, right? So exactly the same we did here is what we will do. As a matter of fact, this function we created, we could have make it better, right? We did it here, we could have put this one also here. Yeah, this is a better way, right? So that we don't need to, we automatically build the model, and then we know the accuracy from the beginning. Yeah, so this is better, right? So we build a model, we already know the accuracy. So if I run this, we know the accuracy already, which is better. And then I can now run this one, and then I know the accuracy. So this is also almost the same, right? Oh, okay, we put it wrong. LR, and we got 0.97, right? Perfect. How do we explain? So the same thing we have done, we can also do the confusion matrix for what we have done together with the classification report, which in this case is going to be my LR, and then perfect, right? So let's do some explanation. How do you explain this model? So before we interpret the model, let's do a simple prediction. I'm going to pick one data set. This is going to be my sample data, which I'll just take my s.test. We will just pick one from the test data. ilog, just any random value, 20, right? And I want to do some prediction. So print, it's going to be LR prediction. We want to predict this one using the LR_CLF.predict. Then this is going to be, there's a simple way, you just pass in the sample data. Right, so if I run this, I did not close it well. Perfect. This one here, and then close it. Right, so we got 0. This is funny. It's funny how we got this value, but we want to make a simple prediction for just one item, right? So that we can actually say, okay, this was the prediction that we had. So we have this one here, I'm surprised we got, okay, let's make it just 0, right? I just want to pick the first one, or we can simply, let's do it like this. I'm surprised it's given us, okay, it gave us a prediction as 0, right? It gave us a prediction as 0, so that means that this is not there's no failure for this. And let's try the same one for the other one, which is going to be ref. So both of them are correct. So how do we explain this particular sample? Why did it give us a value like this, right? So we can explain this model. First, let's do interpretation. So using Outlier 5, so import Outlier 5. Outlier 5 is very useful. Can we use Outlier 5 to do feature importance? Right, so how do we do that? So by this option, we can show from our model which of these are used for prediction, and we can simply do the same thing. There are several ways you can do that. The simplest way is that we can just do the show weight. We just pick in the model, right? We pass in the model that we want with my CLF, the feature, which is going to be the features that we have, and then if I run this, we have, let me make it better. Let's go with the light team. So air temperature, torque, and then a two-way. These are the features, right, that are used to predict, to make a prediction that, okay, there is a failure. So the air temperature, the torque, and the two-way. And there's also some with the rotational speed. You notice that these things are similar to this, right? So there is rotational speed, a lot of outliers here. There is torque, a lot of outliers here. Two-way that did not have this, right? This is what the model is saying to predict that there's a failure. Then we can also try the same thing, another form of feature importance, using permutation importance. So this is one way. The other way is that we can just go with this. So scikit-learn, there's permutation importance. Then we can pass in our model. This is agnostic, right? So this is model agnostic. And then I will just pass in it here, and if I run this, we have similar. So torque is still there. There is rotational speed, right, just like we saw. There is process temperature, air temperature, two-way, and you see that the type is also there somewhere, right? So these are the stuff that are important for our prediction. Now we saw that this one gave us 0, right? So that means that there's no failure. Can we explain this? Yes, we can explain this one using Outlier 5. So let's say explain. I want to explain a single prediction, and it goes with my Outlier 5 that I had. Then I'll just pass in the particular prediction I want to do. So Outlier 5, so show prediction, and I'll pass in my model, regression model, then the sample data that we had, which was my sample data, and then I'll pass in the features. So it's going to be the same thing here. I'm going to get the features, right, that we had for our model, and then I'll close it. So it gave us 0 with a probability of 0.95 with a score of -4. And why did it say that this particular data set there is no failure, right? 0 means there's no failure because there is process temperature, right? And then none of these features that are above here are found here that much, right? They are very low. So that explains why our prediction was that there's no failure. But let's see if there is any data that has a failure. If there is a data that had failure, we can also do that. So I can pick one that has a failure, and then we can just check it out and see that. So let me go back to my test data. This is just simple investigation, and then I want to get any of them, any of my test data that, okay, this, there's no way you can know, right? Because we took out the label, so it's very difficult for you to know. But you can see that this is 2, right? So I can just pick this one, and this is 2. Let's see if, I hope the the iLock is correct. I'm not sure if this is correct, but hopefully it works. No, it doesn't really reach there, right? Because we need to index it. But as you can see, there is a value that has these values here. Right, so we have all of this. So let's go with something like this and see if we can predict. I want to see if this one will work. We are just trying this, if this will work. Okay. In case you have any question or contribution, you can put it inside the comment section below. Of course, there are many ways we can do predictive maintenance, but this is just one of the ways based on the dataset that we have, right? And then I'll just pass in sample data to write something like this. And let's see if we can predict. So can I use this one to make a prediction? Let's try. Hopefully it works. So the reason this will fail is because of how the structure of the data set is, right? So we need to reshape the data set to be in a format that it can be recognized. So one of the ways I can do is like, I can do it like this, which I don't like, but we need to see that you cannot, you have to reshape it, right? You need to reshape it with numpy. So numpy, so np.array so yeah, it gave us the result. Let's check what it said. Sometimes it's good you read errors. It said reshape with this option. So the array -1 1, right? It's supposed to be this option. Yeah, perfect, right? And then since we are reshaping it, I can now try this. And it's still failing. It's funny how it is failing. I was trying to see if we could predict this value. Let's use the LLMs to help us with it. So I'll use the machine learning models, the LLMs that we have around, to be able to allow us to be able to yeah, I'm surprised I'm still getting this value. Yep. So I think the shaping was a problem, right? So I just reshaped it to a better format, and then now it works. And you could see that this is also still, this one gave us a 0, right? That means that there is 0 means that there is still no failure, right? So that is how to do predictive maintenance. So you have learned how to do predictive maintenance from scratch using Python. So what we saw that with predictive maintenance, you can see when there's going to be a breakdown and a type of breakdown. So based on this, we can know the type of breakdown, whether this device is going to have breakdown when it reaches these particular values, right? And then you can also use, in case you have a lot of historical data with time, you can predict when it's going to be having a breakdown, right? So not just the type of breakdown, but when, right? We can also train our model because we already have the types. As you can see, we had the types here. We had the different types. You can actually predict the different type of failure that the device is going to have using these values, right? All you have to do is just change this one, change the label. So all we have to do is just, instead of this one being like machine failure, you can simply do this. Let's try that one quickly. So I'll just change this one, correct this one will stay the same, but it's going to be the failure type. Now we are no more using binary, we are using multi-label classification, and then we can now split the data set as we did earlier on, and then make the prediction again, right? So this is exactly how you can do it. So I'll just copy this one, and we can now make a simple prediction, but a simple model. Don't even need this again. All we need is this, and then we can now build a simple model. So here, let's copy this. We can build a classifier model, and we can also explain the classifier model here. We can just go back again because we already have the same, because this one is similar, right? And then we can also do the same thing for the loss regression model, which was the logistic regression model here. LR, and then we have LR, and this one gave us a different value altogether, right? Then because we have this, we can also make a prediction for the different particular type of classes using the same show weight. So if I go to the show weight like this one here, we can get the type, right? So this one is the type. You can see we have different types, right? So we have the heat dissipation, we have the no failure, we have the OS, that is the stress overstrain failure, power failure, random failure, and then tier, right, failure. So different types of failure together with their what contributes. So the heat, you can see that temperature is very important. The one for the two-way power torque is important, right? You can see here for the random rotational is the highest here, then the two-way is the highest, right? So based on all of the different types of failures, you can see which of these ones are the most important ones. And then you can also apply this same prediction we did here, the same prediction like this one on it to predict and see which of them is going to be. So not just when, but also which type. And you can see from here we have this, right, the highest there, no failure, right? So thank you for watching this tutorial. In case you have any question or contribution, you can put inside the comment section below, and then let me know your opinion about this video. See you another time. Stay blessed.